Okay, welcome back. Welcome back to Petrophysics Rocks. Thanks for coming back and checking out my YouTube channel. This presentation was one that I gave to the very first DevX conference. In fact, it was the one before the very first DevX conference. It was called the Mature Fields Conference back then. DevX is an integrated multidisciplinary conference put together by the geologists and geophysicists, the GESGB as it's called now, and the SPE, Society of Petroleum Engineers, and ourselves, the Aberdeen Formation Evaluation Society, a chapter of the SPWLA, the Society of Petrophysicists and Well Log Analysts. This was my first contribution to DevX efforts. I was working for BP at the time, working on the Magnus field, on the enhanced oil recovery scheme, whereby we took gas from the west of Shetland, pumped it to Sullom Voe, spiked in a few extra goodies, a few extra NGLs, natural gas liquids, and then pumped it out to the Magnus platform in the northern North Sea, and injected it into the ground in what was known as a miscible gas flood. Basically, the gas goes in and is dissolved in the oil blobs, the remaining oil blobs get bigger, and then they can start to flow again, sort of thing. So one of the things that we're interested in when we look at expensive schemes like that is to say, well, what is the size of the prize? How much oil are we leaving behind in our rocks? And one of the things that you could imagine is that in complicated rocks, there might be lots of little nooks and crannies that the oil gets stuck in. And in quite open, clean rocks, you might imagine that we might sweep through. When we flood the reservoir with water, we might flush the oil quite efficiently. So one of the large uncertainties that we have is how much oil do we leave behind so that we can justify what's the size of the prize, how much residual oil target is there for us to go after with these complicated injection schemes. So as I say, this presentation was presented back in 2003. It's a multidisciplinary thing, and we had the opportunity in the Magnus field to actually go and log a well behind the flood front. So we'd already done our business with the water flood. Normally, when you've got an oil field, you pump water down in some wells and you recover, and it pushes all the oil towards your producing wells. And we were able to take the opportunity to log a well that had been flooded, so we could say, okay, how much residual oil is left? How much residual oil are we leaving behind in the rocks? And does that mean there's a big enough prize for us to go after with a gas injection flood? Please, if you take the time to click subscribe, and maybe even drop a comment down below, that would be really appreciated. Get things kicked off more interactively with this petrophysical effort. Maybe I can reach more and more petrophysicists and petrophysicist adjacent type of people, petrophysically curious, as it were. And I'd appreciate it. Any comments that you'd like to leave down below would help the algorithm, as they say. Okay, so this presentation, logging behind the flood front. There we go. I hope you enjoy it. You'll see it's a little bit tricky, and it's not as easy as you might have first thought to measure how much oil we're leaving behind. Okay, thanks a lot for your attention. See you next time. See you soon. Remember, click and subscribe, all that nonsense. Cheers.
Hello, this is my residual oil presentation, logging behind the flood front. Now, residual oil is important at both ends of a field development's life. At the beginning, we obviously need to have an understanding of how much resource we're going to leave behind, so that we can work out what the movable resource is that's going to be available for us to sell. At the end of a field's life, the remaining prize may be large enough to justify a more expensive, perhaps enhanced oil recovery scheme, So therefore, understanding the residual oil, the size of the prize left at the end of a field's life, is obviously quite important. Okay, residual oil on a oil field scale is really a function of two elements. There are the pore scale processes, and those are the ones that we'll be primarily focusing on this presentation, and there are the reservoir scale processes. So we need to understand the pore scale displacement efficiency processes, if you like, how effective we are at getting the oil out of the individual pore spaces. But also we need to understand how the flood front develops, and where, if we pump water into a reservoir to flush oil out of it, where that water goes. Does it contact all of the rock, or does it go through certain pathways, and you get what's called a sweep efficiency measure. That's the key thing you need to know. So where has the water gone, where has it connected the oil and been able to sweep it, and perhaps in other places it may have bypassed it completely. So there's the combination of those two elements, the pore scale processes and the reservoir scale processes, that really add up to giving us our oil field residual oil. Now here at the bottom here I've just shown that we may use this pore scale information to build a permeability map of our reservoir, and if we do some simulation we might see how the flood front progresses through that permeability network. So you see, at those two scales we have to combine everything together to work out what the size of the prize is in our oil field. Now, actually this presentation is an old one. It's really the presentation that I made back in 2003 to the Extending Field Life Conference, which the following year became the first DevEx. So this was a precursor to the DevEx conference that runs annually in Aberdeen, and I did this work when I was at BP, and I thanked the partners then, and I shall thank them now. This data now in the public domain, so I've borrowed it for one of my presentations. Now here as well, just mentioned at the bottom, subsequent to my presentation back in 2003, the DTI became quite interested in some of this work, and they funded a little study to look at the long-term temperature changes from injection seawater as a result of this presentation. I'll probably try and include this on the website as well, but that's what it looks like. It's on their IOR website. I'm not sure whether you can still download it from there, but I'll try and include it on the website anyway. Basically they looked at the data that I presented and kind of did some fancy maths for me, or for themselves, and worked out some of these temperature effects. Anyway, I'll let you peruse that at your leisure. So let's go back to this presentation. As I say, originally 2003. Let's see if I can remember much of it. The overview of the presentation, it was really discussing the Magnus EOR scheme, the Enhanced Oil Recovery Scheme at Magnus, which was the field that I was working on at the time, and I'll show you some overview of that. And then I'll show you some information about the core derived Magnus residual oil relationship. Then we'll have a look at some log derived residual oil measurements and trying to understand some of the uncertainties involved in that, and there's more to that than meets the eye, so I'll take you through some of that as well. And then I'll show you an actual example of a well that we drilled to test out some of these things and attempt to make some measurements of residual oil saturation. And then I'll finish off with the implications of those observations, and also I've added some further summary conclusions at the end as well. Oh, and before we move on, probably I should hit a quick glossary of some of the terms that I'll be using. Remaining oil saturation, that's really the oil that we measure in the reservoir behind the flood front. The SOI is the oil saturation initial conditions, so that's how much oil was initially there, we believe. The SOR is residual oil, and actually there are two types of SOR. SORW, that's the residual oil after a water flood, and SORG is the residual oil after a gas flood. And on the Magnus scheme we had a water flooded field, so we were looking at the SORW, Now you'll have to forgive me, during the commentary of this I tend to just talk about residual oil, and I may neglect to mention whether we're dealing with SORW or SORG, but generally I'll be talking about SORW in this talk. This is the residual oil after the water flood, and so therefore at BP we were very interested in the size of the prize remaining for our EOR miscible gas flooding scheme. We wanted to know how much oil was left after the water flood that we could potentially reduce and produce more of down to a residual oil after gas flood. Okay, here's the Magnus field, just to key you in. At the time I think it was the most northerly UK producing oil field. I don't know whether that's still the case, but either way it's pretty far north, and it's quite a long chopper drive, chopper flight to get out there. And now the interesting thing about the Magnus EOR scheme at the time, now we're looking from the north down towards Scotland. Here over at the west of Shetland we have the Schiehallion oil field, an FPSO development, which one of the byproducts they produce was gas, which we pumped via a pipeline to Lerwick, and then we put some what's called NGLs into that gas. So we put some natural gas liquids into the gas stream to create a special recipe EOR Magnus fluid, and we pumped that out to the Magnus field and injected it into the ground in what was called a miscible gas flood. And the idea behind that was that if you get the PVT properties right, the chemistry right, you can have what's a mixable gas flood. The gas dissolves into the oil, blobs that are left behind, those oil blobs expand and get bigger, and then if you flush that through with an extra pulse of water at the end, those expanded blobs of oil tend to move more easily. So the small blobs of oil that we've left behind after the water flood are enhanced, if you like, and grown a little bit by the gas we're putting in, and then we send a slug of water afterwards to help mop that up. And so that's an enhanced oil recovery scheme. It obviously costs a fair bit of money to do that kind of thing, so you have to be pretty sure or pretty confident in the size of the prize that you've got left. Okay, so from some initial work done at Annex B time, we've got some core flood data. And one of the things about petrophysics that's most confusing is the difficult SW business. 1 minus SW is the oil saturation, and 1 minus SO is the water saturation. And here you may need to pause this menu for a while, sit down with a cup of coffee and work out what these axes are actually saying to you. But in essence, I've tried to summarize it in the red text. We've done some core flood experiments, and at the high initial oil saturations, so that tends to be quite good quality rock, it's got a lot of oil in it, starts out with a lot of oil in it. After we've done our core flood, we find that it has quite a high residual oil saturation left. And actually, what we observe on the experiments as well is that at a low initial oil saturation, this tends to be the poorer quality rock, after we've flooded it we actually get lower residual oil saturations. And I kind of rationalize this to be that it actually, the oil that goes into the poorer rock is obviously in the easiest pore spaces that it can manage, so it sits in the middle of the best pores, so it gets in easily and it comes out easily. Whereas the high oil saturation in the better quality rock, you can manage to squeeze a lot of oil in there and it gets its way into even the smaller pore spaces, and when you flood that out you get what's called snap off, and a lot of oil is left actually in the pore spaces. Now that's a little bit counterintuitive. You kind of think, well, the best quality rock, surely that's going to be flushed the most efficiently, and in some reservoirs that is the case. But when you're trying to analyze observed data or rationalize observed data, this is the rationalization that I came up with, or my view. So we've got low initial oil saturation, low residual oil saturation, because it's easy in and easy out. Okay, so we bear that in mind going forward. So therefore, if we have an understanding of the initial oil saturation through saturation height measurements or capillary pressure understanding, If we know what the initial oil saturation is, we can predict what the residual oil we would expect to be left after water flood is. So we can use that type of relationship to predict what the residual oil will be if we know what the initial oil saturation was. Okay, so that's core, that's quite simple. Now, if we're making log measurements, we're trying to calculate a log saturation using the Archie equation. One of the things that's interesting to look at is, well, how wrong can we be? Now here's a very long Greek type of equation looking at the partial differentials of the Archie equation. Basically what we're doing here is we're looking at what elements that go into the Archie equation, what errors could there possibly be in each term, and how do they add up to an overall uncertainty in the overall SW calculation. Now it's quite complicated maths, but once you work it out and put it into an Excel spreadsheet, my colleague at Shell, Jos Bonny, when I was there, he came up with the use of this 3D Excel chart. I've never seen any other use of this type of Excel chart, but it works pretty well for this, because what we're saying here is that with decreasing porosity, so as the porosity gets smaller, we find that the error in SW actually increases. And actually similarly, with decreasing oil saturation, we see that the error also increases. So at lower oil saturations and at lower porosities, the error in the SW equation, Archie equation, is greater. Now, let me just show you what that means. So we can do a Monte Carlo simulation, if you like. It's a bit easier to set up in an Excel spreadsheet. If we take the oil saturation at initial conditions, 75% oil saturation, which is 25% water saturation, and we look at the typical errors involved in the various elements of the Archie equation. For example, the porosity might be out by plus or minus 1 pu. Perhaps we have a range of RW, maybe there's a 10% error in RT. We're not quite sure of the Archie exponents, and there's an error there, so we plot all those errors together and we put them in a Monte Carlo simulation. What we see that at the initial water saturations, we get an error in the resultant water saturation, a standard deviation, if you like, of plus or minus 5 saturation units. Okay, so at initial water saturation conditions, low water saturation conditions, we get an error of plus or minus 5 saturation units. Now what happens if we look at the error associated at residual oil saturation, so at high water saturations now? Let's have a look what's going on here. We've not changed anything at all in the terms of the errors. We've just said we've got the same number of errors, the same magnitude of errors for each term, but yet we see that at higher water saturations, and all we've changed to do that is we've dropped the resistivity, RT has changed. At higher water saturations we get a much bigger standard deviation error. So I've not changed anything. The only thing that changes is the way that these errors propagate through the Archie equation means that at higher water saturations, a function of the Archie equation is there is more uncertainty. Now, it gets worse, because in the real world we do change things. So here's an analysis using that partial differential approach again at initial water saturation conditions. So here is the element, these are the elements that go into the porosity equation, and these are the errors that I've assumed for the purposes of this exercise. So I've assumed that there's a plus or minus 0.02 gram per cc error in the density measurement. Perhaps in my matrix estimate I can only get the matrix density plus or minus 0.025 grams per cc, and perhaps my error in fluid density prediction, extrapolation, is 0.1 of a gram per cc. Now if I combine all those errors together using this partial differential equation, I get an overall error in porosity of plus or minus 1.95 pu, so essentially 2 pu. So there's a 2 pu porosity error. Now if I plug that down here into my Archie saturation equation, I've got a 2 pu porosity error, I've got a 10% RT error, I've got a slight error in RW, my Archie parameters, maybe they're plus or minus 0.1, and that all adds up to a water saturation error of plus or minus 4 saturation units. Okay, now if we go to our SOR conditions at the end of a water flood, a number of things have changed. So we've still got perhaps the porosity term here is a little bit more uncertain. The row fluid, is it flood water? Is it a mixture of oil, formation water, flood water? There's a bit more uncertainty in the porosity equation. So in fact, my porosity uncertainty, potentially in this case, has increased to 2.5 pu. Also, perhaps in our water saturation equation, there's some uncertainty now of RW, the resistivity of the formation water, because potentially I have a mix of formation water and injection water. So therefore, what is actually downhole? What should I use in my Archie equation? So the error there increases. Similarly, the N measurement in particular, that's the Archie saturation exponent, and you can check out my other Picket Plot Essentials movie to understand that a little bit more. In an imbibition situation, once you've had water displaced by oil by Mother Nature, and then once we've put water back in to flood it, that moves the blobs of oil around a little bit and often increases the saturation exponent. So the error or the uncertainty in the N exponent can be greater. So at the end of a field flood, there is more uncertainty, and you can see that in fact our total error in water saturation is 18 saturation units. Now you can see that if you're chasing a residual oil prize, which means that you've got 80% water saturation plus or minus 20% water saturation error, you have to start to be a little bit careful that you're not what's signal and what's noise. But one of the things that held out a little bit of hope here is that you can see that the biggest error term here is 14 saturation units due to the uncertainty in RW. So therefore, if that's the biggest error, and there are some other big ones in there too, if that's the biggest error, what can we do to reduce that uncertainty in RW and potentially make a valid water saturation measurement of residual oil at SOR conditions? So, what could we do? We planned to drill an injection well in Magnus in 2002. It was close to a previous injector that had been shut in for 9 months, so we were fairly confident we were going to be able to encounter nicely swept reservoir. We were going to log it with LWD and wireline. We were going to take RCI samples. RCI is the Atlas MDT, Schlumberger MDT equivalent. It's a pressure testing tool that allows you to take multiple samples. So we plan to take a number of RW samples through the column so that we could reduce that RW uncertainty that we were concerned about. Now, one of the things we noticed when we drilled the well was that it had about a 3 pu lower porosity than the well nearby, and I think, as I recall, it was the nearby well was only about 90 meters away, so the porosity was a little bit lower, so the quality, therefore, we inferred was a little bit lower than the offset well. And also one of the observations we made that initially was that the remaining oil saturation that we calculated first off was a lot higher than we expected. And in fact that led to some calls to produce the well for a while. They've got more oil here than we expected. So that caused us to start to investigate this well a little bit more closely. So this is our well. And I should probably point out here what we're displaying. Here's a depths in meters, a volumetric display of shale in brown and sand in yellow. Oil is black and the water is pale blue. We have density neutron and sonic logs here, resistivity profile, and if you refer to the Petrophysics for Basics slide, you'll know that the high resistivity over a porous rock must be oil saturation, and we've quantified that here in this column. This is the saturation calculations, and here in this far column we've got a porosity shaded in yellow, and these points here are the RCI pressure points themselves. But one of the things that we noticed when we first logged this well, the high resistivity calculates out quite a high oil saturation. Now let me just go through what these curves mean here. This black curve here is the saturation height function. So that's the predicted oil saturation of geological past, if you like. That's how good the rock is and how much oil it should have held at initial reservoir conditions. This red curve here is the remaining oil saturation. That's the oil saturation that we measure in our well bore today, or I should say 2003 at that time. And this SOR is the residual oil saturation. This green is the predicted residual oil saturation, using that relationship I showed you right at the very beginning, the initial flood measurements made on that Magnus core. So the difference between the green, the residual oil, and the red, the measured oil, this should be movable oil. So this is potentially available to us to produce, and indeed that was the initial expectation that perhaps we could put this well on production. It is actually rather unusual to see quite this sort of intermediate stage saturation halfway between the initial and the residual oil saturation. Generally what tends to happen is once water comes through a reservoir, you get rid of 80% of the oil, you flush it right down, and then you get the majority of the oil is flooded away, if you like, swept away early on, and then it just leaves a few poor volumes for you to strip out later. So this was rather an unusual profile, but nevertheless something that we perhaps considered we should be able to produce. Now, what we do typically in log analysis, we need to know the temperature of the reservoir, the temperature of our borehole, and the fluids therein, so that we can calculate the Archie saturation equation properly. If you refer to my Picket plot essentials presentation, you'll get the gist of this. But this is the typical temperature of Magnus at this depth, around about 3,800 meters. We would anticipate 117 degrees C of formation temperature. So if we assume that temperature, then these are the saturations that we calculate. Now what happens during the drilling of a well is you cool the well down to some degree. There's cooling mud being circulated through the drill bit, cools the bit, lubricates the bit, and circulates back out the hole, and this has the effect of cooling the well bore and indeed the surrounding rock. So that's quite typical. And then what we normally see when we go in with our first wireline run, sometime after the well has stopped drilling and stopped circulating, then the borehole tends to heat up. The cooling mud gradually gets warmer and gets back to formation temperature. And here we see at the bottom here this normal heating effect. So the temperature is increasing at this first wireline run. That's quite normal, that's what we would expect. Then interestingly, on the second run, we see that this normal heating up profile continues down here. So the next run, as I would have expected, increase the temperature down here. But rather interestingly, it showed a further cooling at this depth. So this, rather than the borehole heating up, it appears to be cooling down, which is a bit unusual. Now we can get some temperature measurements from the RCI measurements that we made. Those stations, we can measure what mud temperatures were recorded at the same time we were recording those formation pressures, and we see a profile here as well that indicates there seems to be a decreasing temperature down here. And what I think may be happening is that the mud is cooling down next to this wellbore here, and then there's just sort of sinking down. As it gets more dense, it sinks in the wellbore, so the cool mud sinks slowly through the column. That was my theory anyway. Now we'll take a look in a bit more detail at the water samples that we recovered. What I'm showing you here is the salinities of the 6 RCI samples that we recovered. Magnus waters, the formation waters, are a little bit fresher than seawater. They're around about 20 to 25,000 parts per million NaCl equivalent, and typically seawater is between 32 to 36,000 parts per million NaCl equivalent. So what I've done here is I've highlighted in blue these salinities here, which are consistent with seawater salinities, and in fact 10-iron full chemical analysis sort of confirm that. These are seawater samples, at least predominantly, and these bottom two here are consistent with initial formation water temperatures. Now you may remember that the purpose of this exercise was to determine the residual oil saturation, and to do that we were going to make these RW measurements to reduce the uncertainty in RW. So what RW should we use in our Archie equation? Well, there you go, you've got 6 of them, and those are the RWs that you should use in your Archie equation. No doubt about that, no uncertainty there then. So once you use those salinities in your Archie equation, lo and behold, you calculate oil saturation, more oil saturation, because you're using a more saline water predominantly. And what's interesting to note is actually that the saturation, the logged remaining oil saturation, overlays pretty well with the predicted oil saturation from the saturation height curve. So what this is saying is that the apparent log saturation is consistent, would be consistent for this quality rock with that initial oil saturation. So you've got one piece of evidence there saying actually this oil column hasn't been swept at all, it's at initial oil saturation conditions. So that's good, we can produce that, can't we? But yet there's a problem. We've already said that we've got seawater here. That's what the water chemistry says. We've got seawater. Well, how did that seawater get there if there's no sweep? So obviously there's a bit of a conundrum there. You can't have seawater and unswept reservoir by definition. So there was something else going on. So we returned to have a look at this temperature story. What was going on with that temperature? Well, one of the things that we thought was, let's see if the temperature is cooling down, perhaps somehow we're wrong with our formation temperature. So we rushed around to get a temperature tool sent offshore in the 14 days between logging this well and the time they were ready to perforate it and complete it. So after we logged the well, we cased it and completed it and ran the completion and everything, and that took about 14 days, and then we could make our temperature measurement. And lo and behold, here we do see these various G's. In fact, we've got 2 temperature runs of 2 different tools just to confirm it. We do see this temperature profile here. So we are down at 33 degrees centigrade, which is not very hot in terms of formation temperatures. It's about a spring day in Muscat, where I used to work actually. So it's not very hot, and it seems to be that the temperature is equilibrated to the true formation temperature. So this formation is genuinely down at 33 degrees C, when really normal Magnus rock would have been up at what was that I said before, 117 degrees C, I think. So the rock has been cooled quite considerably. So we've got the right water salinities to use in our equation. So if we correct those with our the correct temperature profile, so we use a temperature profile, and then we calculate our new Archie saturation, lo and behold, all of that spurious oil saturation is lost, is reduced, and we get back towards our expected residual oil saturation levels. Let me just toggle between those two a little bit, and you can see that by using the correct temperature and the RCI water salinities, now we're starting to get back to what we had anticipated to be the correct residual oil saturations, and that's all consistent. We've got seawater here, and we've got this temperature effect going on as well. That's quite dramatic. So if we zoom in a little bit on this well, this is the initial data set that we got, the LWD data set. Unfortunately, we weren't able to download the memory data from the tool, so we've only got this real-time data available, which means it's not quite as high resolution as we'd normally expect. But a couple of things that I would like to point out is that on this resistivity profile here we see quite a large separation in resistivity. Now it's quite normal to see resistivity separations in terms of oil-based mud or filtrate invasion profiles, but generally it's my experience that I don't tend to see any sort of invasion type profiles occur at initial LWD times. Generally the LWD measurement is just made an hour or so after the bit has passed, and there isn't really sufficient time to develop a proper mud filtrate derived resistivity separation profile. There are other reasons why you can get separation profiles on LWD tools, in particular geometric effects, geosteering effects, but it's quite unusual to see what you might interpret as resistivity invasion profiling effects. And indeed, if you look at the bottom section here and the upper intervals here, they overlay reasonably well. So this separation here is quite unusual. So the deep reading tool has high resistivity and the shallow reading tool has a lower resistivity. And I'm kind of thinking that perhaps actually out in the deep reservoir, now with that temperature knowledge, is actually colder rock, and in the shallower reading tool closer to the borehole wall is actually effectively relatively heated up, and so therefore that's lower resistivity. Perhaps you're not convinced by that, but let's add some more layers of evidence on there. You may not be convinced by this either. Here is the porosity log, the density log, and I've put a red line over there, what I've called the maximum porosity interval. Now if we compare that to the wireline log that's run a day or so later, I think, you see that the porosity actually decreases a little bit between wireline and LWD. Let me just toggle between the two. You see it's reasonably constant down here, but yet there seems to be, over this interval with the enhanced separation, there seems to be a genuine movement. And of course there's a resolution difference, and you may not be that convinced by it, but generally there's a 1 or 2 PU shift, but yet elsewhere in the well the density, LWD and wireline overlay very well. So that seems to indicate to me, and I'm wondering again about this temperature effect. The wireline tool is recorded later on when the wellbore is cooler. Perhaps the rock has contracted a little bit, so it's a bit more stiff. Here as well, actually, I'm overlaying the LWD, the wireline resistivity, and you see the wireline resistivity overlays very well with the shallowest LWD density, and there's a bit of a difference here to the deepest tool. Again, perhaps you're not convinced by that. But one of the interesting things we did with the sonic log, we ran a shear sonic log in this well, and on Magnus we have a pretty good handle on the relationship between compressional and shear velocity. And it's normal for petrophysicists to have to calculate shear velocity logs for their geophysical colleagues, and so we've got some well-established equations that go, given a compressional wave, what is the shear velocity. Now it's interesting in this particular well that if you take the shear velocity and back calculate a compressional velocity, you notice a couple of interesting features on the log. So first of all, the shear velocity is less dependent on fluid effects. Basically, shear waves can't be propagated through fluids, so therefore the dominant effect of dominant control on shear velocity is the rigidity of the rock, its ability to transmit sonic waves through the fabric of the rock, and it's less affected by fluid effects. The compressional wave is affected by both fluid and solids. But if we take that shear log and back calculate a compressional log, one of the things you might notice here is that over these intervals here, which you may recall were the normally temperatured zones, there's quite a good agreement between the predicted compressional from shear and the actual measured compressional. The curves overlay quite well. Whereas over this interval here, the expected compressional velocity from our shear tool is much faster than we'd expect. So given the shear log in this well, we would anticipate this magenta dashed compressional line. but yet what we see is this recorded red solid line, and it's actually much faster than we would have anticipated. And in fact that goes opposite to a fluid effect actually. So the log has got faster, and now if that is a temperature effect, it must be due to the framework getting more rigid, more faster, transmitting sound waves more quickly, because actually if you cool fluids down, they actually get slower velocities. The fluid velocity would go the other way. So I'm pretty confident that this effect must be primarily due to the framework, the rock fabric, rather than any cold fluid effect, if you like. So in fact, because that would work against it. So that's interesting, but it's just interesting that this discrepancy ties in with that temperature anomaly, that 33 degrees C rock. So to my mind, it's quite a significant compressional change. Perhaps you would say that the density one is less convincing, but again you've lost a couple of PU density over the LWD, and remember it's also 3 PU lower than the offset well, which is only 90 meters away, and most geologists would say there's no reason why the geology should change that much. So I think the conclusion we came to at the time was actually this log we measured at 3 PU less porosity than we expected, and I don't think it's geological. I think it's also related to this fluid effects and these temperature effects. So, the implications of these observations then. Well, these thermal effects in water-flooded reservoirs can be dramatic, as we've seen, and also long-lived. Over 9 months had elapsed between any fluids in or out of this area, and yet still the reservoir was down at 33 degrees C. Now, one of the interesting things is a rule of thumb: if you inject water into a reservoir and cool that reservoir down, the water front will proceed, and as a rule of thumb, the thermal front behind it will cool down, and it'll travel at about a third of the speed. So if you look at an injection halo around a well, roughly look for something else about a third of the way out, and that will be roughly where the thermal front is, because the thermal changes by conduction mechanisms rather than convection mechanisms. And if you read that DTI paper that I referenced earlier on, I'm sure they'll give you a lot more detail about that. But I remember it was quite a surprise to me, certainly at that time, that the temperature could still be so low after such a long time. So obviously this has an impact on measuring residual oil from resistivity measurements, so if you don't know what your temperature profile is, it can have quite a big effect. So if you're drilling a well, I've said that I like to drill wells behind waterfronts, floods, but you've got to make sure that you're either out in front of the thermal front, or if you're behind it, then you need to get a static temperature survey just to confirm, because as well as your RW uncertainty, you've now got a big temperature uncertainty. Also, I would have thought that this kind of thing would have potentially large impacts on 4D seismic interpretation. The sonic and the density indicate an increasing hardness. So when you see those pretty pictures of halos around water injectors, saturation change measurements and pressure change effects are reasonably well understood and well documented, but perhaps there is also potentially a large impact of a delta strain, a change in the stress regime because of this thermal contraction that goes on, and you've seen quite a large shift in compressional velocity there. Now, to my mind, that could have quite a large effect on 4D seismic interpretation. So in addition to the traditional saturation and pressure measurements that we have to take into account, perhaps we also really need to start thinking about those temperature gradients in particularly well water flooded fields. One of the concerns we had at the time for BP on their EOR flood was this miscibility issue, the degree of mixing of the gas. You've got to be able to get the right pressure, temperature and PVT properties right, the chemistry right, to make sure that the gas is dissolvable in the oil, and there's an optimum set of conditions for that to happen. So you've got to be careful and got to be aware of these temperature effects, and also future thermal frac propagation. When we inject water into reservoirs, typically we often rely or expect or benefit from thermal fractures being set up, pumping down cold seawater into hot rock, and actually that cracks the rock and helps you get increased injection rates away. Now, if you're going into drill injectors into previously swept areas that are potentially behind thermal flood front, then you've got to be careful. You've got to be sure that do you have sufficient permeability in the matrix to be able to get all the water away that you need, because you might not be able to initiate new thermal fractures. Cold water into cold rock may not be enough to get you your expected benefits. So don't count on your thermal chickens until they're... Oh, I'll stop that analogy there. Okay, and also one for the drillers, if you're planning to complete wells behind the thermal front, and therefore I would have imagined that your cement recipe would have to be varied quite considerably if you're dealing with 33 degree C rock. But anyway, this was primarily supposed to be a residual oil presentation, not necessarily a thermal one, although it turned into a bit of a thermal one. So the conclusions that I'm currently coming to as a quantification of residual oil involves a lot more areas of uncertainty than at first thought. Once you sit down and think about all the things that you don't know, then it gets scary quite quickly. Nevertheless, despite all these uncertainties, it's my current view that I would rather still be logging in open hole with behind an established flood front with RFT water samples, so that I can reduce that uncertainty on sweep water to formation water mixed. To me, there are a lot of uncertainties, as I've demonstrated, but at least you have a chance of getting to the bottom of them, and this would still be my preferred way of doing things. Coring behind the flood front, some people spend a lot of money on residual oil core, perhaps swapping out muds to water-based muds, which I think you probably have to do. When I've seen this done in oil-based muds and attempted to dope oil-based muds, the wettability effects are such that the preferential oil wetting means that I don't think you get a good residual oil saturation if you're putting potential oil-based mud filtrate back in there, no matter how much you dope it. So I think you have to go water-based mud, and then of course that's still difficult and expensive, and then even once you've got that data, you still have issues about how to correct that back to representative reservoir conditions. I think you can do it, but you need to be really sure what you're doing. You need a lot of planning, a lot of effort, and as I said, a lot of expense. Cased hole methods. It's my view that RSTs, those carbon oxygen logs and sigma logs, pulse neutron capture tools, cased hole resistivities, even cased hole resistivity, there's a lot more interpretation goes into that than you might think. Depth of investigation issues and things like that. So I think there's a lot of uncertainty there, so I'm still an open hole kind of a guy. I'd still rather be measuring open hole measurements rather than trying to interpret cased hole measurements on some of this stuff when the error bars are so big. Perhaps the log techniques do hold out hope, but you've got to wonder how representative they are of conditions out in the reservoir as well. In the laboratory, when you've got core floods and you need to bump up the volume rates, bump up the rates to get that final bit of displacement and doing what's called a bump flood, you're stripping things out through viscous effects that perhaps you wouldn't necessarily see out in the reservoir at your 1 foot reservoir advancement flood front per day kind of issue. Anyway, these are just my current views. That's the beauty of petrophysics, I guess, and the beauty of this job is that you're always learning all the time. I may have different views tomorrow, but at least I'm hoping that I've given you some insights to some of the issues that I had to deal with. So I would be happy to hear your views and anybody else's opinions on what's flavour of the month. But hopefully you've enjoyed this presentation. I've gone on a little bit too long again. I do apologise for that, but you never stop learning in this business, and hopefully I'll pick up a few more tips along the way too. Okay, thank you very much for your attention.